Welcome to this session for Arduino based systems. In today's session we will try to go through some very simple points on combinational circuits, since it is so obvious that the gates and all these things are quite simple. They can be self-learned also. So we first focused on sequential circuits, but some points of combination circuits which are required in our general studies we shall go through. Combinational circuits simply consist of interconnections of gates to each other and cascading them with no feedback. The difference between sequential and combinational circuit is that sequential circuits have at least one feedback link, means some of the output goes back to input stage, and for combinational circuit there is no feedback. In today's session we shall cover adder, multiplexer and decoder. Subtractor right now we don't discuss, we will elaborate it at some other point. So adder, multiplexer and decoder would be there for mid-semester examination. These are very simple circuits. So just interconnection of gates. So a combinational circuit, what is the property of combinational circuit? The property of combinational circuit is that it is having a set of inputs. We can say, let us say A, B, C, D, A, B, C, D, etc. A set of outputs which we can say as Y0, Y1, Y2, and for a given combination of inputs we get a given combination of outputs, and it is unique, means a particular given combination will always result into same output combination, whereas in case of sequential circuit it depends on state. So various combinational circuits, for what combination of input you want what combination of output, depending upon that various combination circuits have been thought over. The basic circuits, that is gates, AND gate, OR gate, NOT gate, XOR gate, is quite obvious, there is no need to explain that, everybody of you know it. OR gate, AND gate, NOT gate and XOR gate. Now using these gates we go for constructing a simple circuit called as adder. In binary arithmetic, you know that I think that the binary arithmetic is now something which is quite simple. In binary arithmetic, you know that 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0 and carry 1. Or in fact, actually I should have written it like this. I think it is quite simple, just like a primary school arithmetic. When we add 0 plus 0, answer is 0. 0 plus 1, answer is 1. 1 plus 0, answer is 1. And 1 plus 1, we have answer is 0 and we get carry. So addition of two 1-bit number when both are 1 is a 2-bit number. So carry is 1. So this is called as, so in any case we can say that when we add 2 bits, we get a, when we add 2 single bits, we get a 2-bit result. Of them, this is called as sum and this is called as carry. This input is A, this input is B. So now we want to construct a small circuit, very small circuit called as half adder, which is having inputs as A and B and outputs as carry and sum. Inputs as A and B, outputs as carry and sum. So what we want? When A and B, we can write a truth table, sum and carry. When A is 0, B is 0, sum is 0, carry is 0. When A is 0, B is 1, sum is 1, carry is 0. When A is 1, B is 0, sum is 1, carry is 0. When A is 1, B is 1, sum is 0 and carry is 1. So quite simple and obvious. So you can look at sum column separately and carry column separately. So how will you design a circuit inside? So we want to design, I think this is very simple, we should not even spending unnecessary time on simpler things is non-optimal utilization of time. So we try to finish it at a very somewhat comparatively rapid rate than other complex themes. So if you look at A equal to 0, B equal to 0, carry equal to 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. So how can you think of a carry bit? When A and B both are 1, carry is 1. When A and B are both 1, carry is 1. So there is no need to explain how should I design. Simply we can say that there is one AND gate is there to which both inputs A and B are connected. So one AND gate will give me carry of 2-bit addition. And somewhat is the situation when both are 0, answer is 0. When both are 1, still answer is 0. When 1 is 0 and 1 is 1, answer is 1. When 1 is 1, other is 0, answer is 1. This is called as, this is the truth table of what? XOR gate. So XOR gate, what XOR gate tells that if only one of the inputs is 1, OR gate, if one input is 1, output is 1. And for XOR gate, if any one of them is exclusively 1, exclusive OR. If only one of the inputs is 1, then the output is 1. If both are same, output is 0. XOR gate tells that if both inputs are same, output is 0. If both inputs are different, output is 1. So we find that the sum column is XOR gate. 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1. So you simply put one XOR gate here and XORing of the inputs will give me sum. This is called as half adder. This is called as half adder. Why half adder? HA or half adder. Why half? Because it adds 2 bits, produces sum and carry. It is called as half. Why it is called as half adder? That I will explain when we go for discussing full adder. Is it clear now? Half adder, 2 input bits, sum output, carry output. Now, suppose if we want to add 2 2-bit numbers, say 1 0 plus 1 1 we want to add, or we can say 1 1 and 0 1 we want to add. How do we add this? 1 plus 1, sum 0 and carry 1. Now, when we are adding 2 numbers, you can think of this in conventional addition, where you are adding 2 numbers, multiple digit. When you add first least significant digit, you add only 2 digits. And when carry is there, you have to take carry and add carry and next digits of both numbers. So while performing addition of 2 numbers, we have to perform addition of 2 digits for the LSB and 3 digits for next, what we can say, digits depending upon the carry coming from previous digits. So when we think of adder, we should not think of only 2 bits to be added, 2 bits and previous carry coming into picture. So here what we are going to add? So this number is A, this number is B. So this bit is A0, this bit is A1, this bit is B0, this bit is B1. So when we add A0 plus B0 is sum 0. At that time carry 0 is produced. So A1 plus B1 plus carry 0 is sum 1 and next carry 1 and this carry 1 is, so this is a 3-bit answer. So addition of 2-bit numbers is a 3-bit number, wherein in each case we have to add 2 bits first, and while going for adding next bits, carry coming out from first addition needs to be taken into consideration. So here I have to add A1, B1 and C0. So 3 bits are to be added. So in that case what I do is I want a full adder wherein I should have one bit A, one bit of B, and now I give some name change C in, carry coming from previous one, and what I generate is C out and sum. This is 0, it is C in, I say C out, so it creates clarity. So what's the truth table? Truth table is very simple. We can generate a truth table. So in general, when I say adder, we should have addition, provision for addition of 3 input pins, A, B and carry in, and output pins are sum and carry out. So a truth table contains 3 input columns, A, B, C in, or to be better, this is not wrong, but we write it in reverse way. We write C in, this is C out, this is sum. We write C in A and B, and output is C out and S. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So it is very simple. You have to simply add and tell what it should be. When 0 0 0, C out is 0, sum is 0. When 0 0 1 you add, the answer is 1 and carry is 0. 0 1 0 you add 1 and carry is 0. 0 1 1, so 1 1 sum gets 0 and carry is there. 1 0 0, again this is 1 and this is 0. 1 0 1, so when 2 bits are 1, they add to 0 and we get a carry. 1 1 0, they add to 0 and we get a carry. And 1 1 and 1. So 1 1 and 1, what happens? 1 plus 1 is 0. 1 plus 1 is 0. A carry is generated. So carry is 1. And in that again 1 is 1. So this is the truth table. So this is the truth table of full adder. This is the truth table of full adder. This is the truth table of full adder. So what is the answer of this? When there are odd number of ones, sum is 1. When there are even number of ones, sum is 0. And what about carry? Carry is generated if 2 or more ones are there. Is the idea clear? सगळ्यात सोपा आहे, मराठीत सांगतो. सम कधी 1 असते, त्या 3 जे बिट्स ज्याची मला बेरीज करायची आहे त्यातली ऑड नंबर ऑफ बिट्स जर का 1 असतील तर सम 1 असते. इवन नंबर ऑफ बिट्स 1 असतील तर सम 0 असते. आणि कॅरी कधी 1 असतो, जर जे नंबर्स मला ऍड करायचे त्यातले 2 किंवा 2 पेक्षा जास्त बिट्स 1 असतील तर कॅरी 1 असतो. राईट. सो हियर नो वन्स, number of ones 0, sum 0, number of ones less than 2, carry 0. Number of ones odd, sum someone, number of ones less than 2, carry 0. Number of ones or someone, number of ones less than 2, carry 0. Number of ones even, sum 0. And number of ones 2 or more, carry 1. Number of ones 1, that is odd, sum 1, number of ones less than 2, carry 0. Number of ones 2, so even, carry sum 0, but number of ones 2 or more, carry 1. Number of ones 2, that is even, sum 0, number of ones 2 or more, carry 1. Number of ones 3, it is odd, so sum 1, and number of ones more than 2 or 2 or more, carry 1. So this is called as full adder. This is called as full adder. And then suppose, how can you, so using a full adder, how can you generate cascade then? This is a full adder. This full adder can be converted, this full adder can be designed by using some kind of gates and half adders. So that I will give as a homework, not so important. You can use 2 half adders and OR gate to prepare a full adder. But you can use 2 half adders and 1 OR gate to prepare a full adder. Now, if I want to prepare a 4-bit adder, how I can do that? If I want to prepare a 4-bit adder, how can I do that? That is quite simple. I take full adder, I take next full adder, I take next full adder, I take next full adder. I have got 4 full adders. I have got 4 full adders. How do I add 2 4-bit numbers? What is the procedure of adding 2 4-bit numbers? Suppose if I add like this, 0 1 0 1 plus 1 1 0 1. How I do? While adding, I only have these 2 bits. So this plus this, 1 plus 1 0, carry 1. 0 plus 0 plus 1, 1 carry 0. 1 plus 1 plus 0, 0 carry 1. 1 plus 1 plus 0, 0 carry 1, and this is the answer. So how I do? Here there is no carry. Here there is no carry. Carry in is there, which is 0 in this case. So this carry at the beginning of the addition of least significant is always 0. This will be taken 0. So each of them, this bit is A0, B0. This is A, this is B. A0, A1, A2, A3. Each of them is having carry in. Carry in. This is A, B, carry in. A, B, carry in. And each is having carry out also. Each full adder is having C out. Each full adder is having S. S. S, S, and carry out, carry in, very Very simple. Just take over the carries to next. So carry out of this is carrying of the next. Carry out of this is carrying of the next. Carry out of this is carrying of the next. And last carry out is the next bit. This is sum 3, S2, S1 and S0, and this is last carry out coming into picture. So total 5 bits of the answer are this. So addition of A3 to A0, A3, A2, A1, A0 plus B3, B2, B1, B0, we get S0, S1, S2, S3 and next carry. And this carry is to be grounded. So in general, a 4-bit binary adder will have got the inputs as 4 inputs, 4 other inputs, A3, A2, A1, A0, then B3, B2, B1, B0, then outputs as S3, S2, S1 and S0, input as carry in and overall output as carry out. So a 4-bit binary adder comprises of 2 4-bit inputs A and B, 1 4-bit output sum, 1 carry in and 1 carry out. So if I want to prepare 8-bit binary adder, then you take this one, have one more, carry out of previous is to be connected to carry into the next. So in this way you can cascade it to any number of lengths so that you can get a longer adder. So I think this is quite enough and quite simple also. There is nothing new. Now we go for next part, that is the multiplexer. The next part, that is multiplexer. Multiplexer is a very simple circuit, it is many into one. So you are having a multiplex theaters wherein you can go and watch whatever you want. Multiple inputs are available to you. You can choose whatever you want. That is the concept of multiplex. So here in general a multiplexer consists of more than one inputs. What multiplexer is? More than one inputs and one output. Multiplexer consists of more than one inputs and one output. So output is Y. Output of multiplexer is denoted by Y. Output of multiplexer is denoted by Y and it is having multiple inputs which are denoted by inputs I0 and at least 2, we start with I1. So we have 2 inputs I0 and I1 and one output Y. Then the multiplexer can be set into a scenario where it is having 2 inputs. Which input should occur on this output is selected by, called as select line S, and we get S0 select line. So this select line selects which input should come on the output, and the truth table of multiplexer is very simple. the select line 0, I will give given specific number 0 and output y. If the select line 0 is 0, output y is I0, and if select line is 1, output is I1. So multiplexer, this is, and how many input lines are there? 2. So this is called as 2:1 multiplexer. 2:1 multiplexer. There are 2 input lines, and depending upon select line, what input occurs or appears on output is decided. So if S0 is equal to 0, Y is I0. If S0 is equal to 1, Y is I1. And how the circuit is designed? Circuit of this is very simple. We have got I0. We are having an AND gate. We have got I1. We have an AND gate. And we have an OR gate. It's quite simple. There is no rocket science here. And this is Y. And this is S0. So what will happen? If this S0 is 0, we can have, what will happen if this S0 is 0? This will be 0, as this is 0. This will be 1. When for AND gate, one input is 1, what is AND gate output? ANDing of these two. So in this case, this is 0. So irrespective of anything, this will be 0. In this case, this is 1. So ANDing would be I0. So for this OR gate, what we are having? 0 is one input, I0 is other input. So what is output? I0. So when S0 is 0, output is I0. I will write with next blue color. When S0 is 1, what will happen? This would be 1, this would be 0. So as this is 0, this would be 0. As this is 1, this would be I1, right? Or if you get confused, then I will rub this out. So when S0 is 1, what will happen? This is 1. This pin is 1. This pin is 0. This, as this is 0, this will be 0. And as this is 1, this will be I1. This will be I1. And at the output, I will be getting I1. At the output, I will be getting I1. So this is 2:1 multiplexer using one select line. This select line 0, I0 appears on Y. Select line 1, I1 appears on Y. This is a multiplexer, many as to 1. And the simple most option is 2:1. Now we will go for designing a next multiplexer as 4:1 multiplexer. We go on designing a 4:1 multiplexer, for which we use 2:1 multiplexers blocks. So what I want one 4:1 multiplexer. It will have how many input lines? I0, I1, I2, I3. What is the output? Y. But how many select lines should be there? To select out of 4 combination. So in general, if a multiplexer consists of 2:n input lines and 1 output line and n select, so a 2:n:1 multiplexer consists of 2:n input lines, 1 output line and n select lines, and n select lines. So for a 4:1 multiplexer, 4 input, 1 output, and how many select? 4:2. So 2 select lines. So there will be S0 and S1. S1 and S0. One is most significant bit, 0 is least significant bit. So what should the truth table of this multiplexer? Truth table of this multiplexer would be S1, S0 and Y. If S1 is 0, 0, 0, I0 appears on Y. If S1 is 0, 0, 1, I1 appears on Y. If S1 is 0, 1, 0, I2 appears on Y. If both are 1, 1, I3 appears on Y. I3 appears on Y. Now what I will do, how I can design this? I will have one 2s1 multiplexer, other 2s1 multiplexer, and one more 2s1. I will have, this is here, each of them is having S, I0, I1. These are local names inside. I0, I1, Y, I0, I1, Y. So this is a very simple circuit. There are 3 multiplexers, 1, 2 and 3. So this is the final multiplexer. So what appears? This output will appear here. Now if this select line 1 is 0, what will happen? This will appear here. If this select line is 1, this will appear here. And means this select line S0 is given here also, here also, here also, here also. So when S0 is 0, what will happen? It will select I0, this I0 will appear here. If when S0 is 1, this I1 will appear here. At the same time, the same S0 is given here also. So when S0 is 0, I0 appears here and I2 appears here. Then whether I0 should finally appear or I1 should appear. If you find that these names are confused, if you find that these names are internal, or you can use them if these are confusing, then you can use them as A and B also. So that I0, I1 should not be a problem. So when select line is 0, this appears. When select line is 1, this appears here. So now when S1 is 0, this S1 is given as select line to final multiplexer. So this final multiplexer will choose output of this multiplexer or output of this multiplexer. Output of this multiplexer is either this or this. Output of this multiplexer is either this or this. So S0, this select line will decide this multiplexer should give this or this on its output. It also decides what this multiplexer should give, whether this or this on this output. So when we can have all possible combinations, when S1 is 1, when S1 is 0, what happens? When S1 is 0, top multiplexer output comes on final output. When S1 is 0, top multiplexer output appears on final output. And what is top multiplexer output? Top multiplexer output is decided by S0. So when S1 is 0, this will appear here. So when S1 is 0, what appears? Either I0, if I divide this part, when S1 is 0, S0 decides what should be here. When S1 is 0, this appears here, and that time if S0 is 0, I0 appears here, it appears here. When S0 is 1, I1 appears here, this appears here. When S1 is 1, bottom multiplexer, bottom mux output appears on final output. When S1 is 1, this bottom multiplexer output appears here. So when S1 is 1, this will appear here. That time if S0 is 0, when S0 is 0, I2 appears here, and when S1 is 1, that one will appear here. S1 1, S0 1, S0 1, I3 appears here, S1 1, this appears here. So we have got 3 multiplexers, 2 multiplexers in the first layer and 1 final multiplexer. So S1 bit decides which multiplexer output should come at the total output, and S0 bit decides which of the 2 inputs should come on the outputs of first layer multiplexers. Is the idea clear? So S0 selects one of this here and one of this here, and this selects either this or this on the final output. So when S1 is 1, when S1 is 0, this appears here. When S1 is 1, this appears here. When S0 is 0, this appears here and this appears here. When S0 is 1, this appears here and this appears here. So S0 decides which individual input should appear on outputs of first layer multiplexers, and S1 decides which multiplexer output should appear on final output of the multiplexer. So this is called as 4:1 multiplexer. 4:1 multiplexer having 2 select lines, 4 input lines. So these two, when these two are 0 0, this appears here. 0 1, this appears here. 1 0, this appears here. 1 1, this appears here. So the multiplexer is 2 raised to n as to 1 multiplexer, 2 raised to n input lines, 2 raised to n input lines, 1 output line, and n select lines. I think for today's it is more than enough. We shall discuss the demultiplexer part in the next session. Thank you.